All right, so Johan, welcome to the Able Tasman virtually as patron of our great expedition. It's wonderful to have the connection here. We're currently in a place called Willis Bay, which is on the Prince of Wales Island, right in the heart of the Northwest Passage. We'll give an update about the journey to date and how far we've gone and some of the experiences. But it's obviously your two great sons, Isak to my left as both captain and your eldest son, and to my right, Alex is your second son and first mate. And I think you're calling in from Stockholm.
That's right. I'm calling in from the archipelago outside of Stockholm, and it's great to follow your progress. I can tell you, we start every day here, logging on to the Able Tasman Sail and Science Ocean Expedition homepage. It's just amazing to see how detailed and up to date we can follow your position on the web page, and how you're following through the whole Northwest Passage sail and crossing all these tipping point systems. So it's great to see, and fantastic they were able to make your way through this bottleneck just the last few days. What was it called? The Barents Strait, or
Ballot Strait.
yeah, yeah,
Yeah,
quite something.
yeah, the Bellot Strait is quite amazing. It's this tiny channel. I think it's about how wide is it? About 2 kilometers?
About a kilometer.
Yeah, about a kilometer wide, about 17 miles long, and
Mm,
and it's the northernmost point. The southern point of it is the northernmost point of the Americas. So in a contiguous way. So it's quite a compelling spot in the whole Northwest Passage. It's got amazing currents and winds going through it. We got through there very well. And yeah, so it's a very significant spot that we're in. By the way, talking about following us, I'm a bit of a nerd about maps, and behind you can see here some of the old maps from I think the 16th century and
mm,
beyond. And it reminds me of what all the old explorers were doing, which was to actually explore and document where the land is, just to find out, the exploration of land. I guess what we look at this expedition as being is very much an exploration of not the land itself, but of the science and the impacts that humans are having, and the role that the Arctic plays in the global Earth systems, and therefore the impact that it has on humanity. And so we're very proud of what role you're playing, and Isak and Alex as well, as part of that vision, that project, and to try and bring this in a way that people can really relate to and understand. And as you say, follow us on the way. They can log on
mm.
onto the website and onto other social media, and to really follow that journey and those experiences, to which we'd love to share with you, because obviously we're on the ground and on the water here, and
Mm.
seeing things that you've been such a great leading scientist about. And a big theme of this expedition is about the planetary tipping points, of which I'd love you to talk about, but of which 16, I believe, have been identified globally, and 6 of those are in the region through which we're traveling. We've started obviously from Norway to Iceland to Greenland, up the west coast of Greenland, and through the Northwest Passage, we end up in Alaska. And through this entire region, we're passing through 6 of these tipping points. So maybe we can start there, Johan, given that you've been such a great thought leader and scientist around tipping points, and to just talk briefly about what are tipping points, and give some examples of them, and how they work.
Yeah, and absolutely. And then I think just to kind of frame the tipping point description, I think it is good for everyone who listens in on this, that you are, I mean, not only passing through the Northwest Passage, which has been impassable for a large part of humanity's existence on planet Earth, and it's today opening up because it is the most rapidly changing biome and region on planet Earth. I mean, we can today scientifically even define the location where you are as Earth's ground zero. is warming 2 to 3 times faster than the planet as a whole. And we know today, and we learn more and more, that the Arctic is connected with tipping element systems, with weather systems, with sea level rise, with even all the way down to Antarctica through different cascade connections. So basically, domino effects originating from the Arctic. So not only do you have most rapid changes in the Arctic, not only do you have 6 big tipping point systems, but we also understand increasingly that they are connected across the entire planet. So basically, you're sitting there in the engine room for a significant part of the stability of the entire planet. So that is why it's so important to understand and to learn from the Arctic region. And what is a tipping point? Well, a tipping point, to start with, I think it's good to just zoom out even there to recognize that we understand today that the state of the planet is determined by the state of large biological, chemical, and physical systems on Earth, and that these systems, like the Greenland Ice Sheet, like the Arctic sea ice, like the permafrost systems, like the Amazon rainforest, can exist in multiple stable states. So you can think of them as having different attractors where they stay stable. And these stability domains, a very classic example is that you can have a rainforest, but if you push that system too far across a tipping point, it will irreversibly shift and turn into a savanna. And if you push that system too far, it will irreversibly shift and become a desert. And the same thing with an ice sheet. An ice sheet can be a very stable slab of ice, but if you push it too far through environmental change, you will irreversibly shift it into an unstoppable melting, and it will ultimately become an open water surface. And what is it that determines whether the system goes from one stable state to another are the feedbacks. So what we scientifically always are looking for on every tipping point system are what are the dominating feedbacks that keeps the system in the stable state, its stable original state. And for all the systems that you're sailing through the Northwest Passage, the by far dominating systems that, by the way, Isak and Alex are more experts on than I am, is albedo. It's the physical functioning of ice surfaces determined by their color. So a permanent stable ice sheet is a very white, light color, reflecting back some 90% of incoming solar radiation, bouncing it back into space, and basically allowing the system to be self-cooling. But there's a second feedback system where you are, which is often not discussed, which is the altitude. The fact that the Greenland Ice Sheet itself is over 3,000 meters of a slab of ice. So, well, you know this, Keith, better than anyone. You walk up a mountain and it gets colder. And so, of course, an ice sheet that melts, it's like walking down a mountain. And these are the two dominating feedbacks, the reflectivity of a white surface and the elevation of ice. A white surface, which is very high, is stable. It keeps cool. It is the state that the ice sheets, all the ice sheets that you're passing through, all the tipping point systems that you're sailing through, have been in one basin of attraction since we left the last ice age. So for 12,000 years, you've had a stable Greenland ice sheet dominated by this cooling reflectivity, 90% of heat going back to space, high altitude, really cold. This becomes self-cooling. It's a stable, cooling state. Same with the permafrost, same with the AMOC, same with the Labrador sea current, same with the Barents Sea ice. We can go through these 6 tipping point systems that you're sailing through. Then we start burning fossil fuels. We release greenhouse gases. We cut down trees. We destroy biodiversity. The planet warms up. And at a very precise point, you come to this shift point, the tipping point, where each of these, they have different temperature points for it, but each of these tipping element systems have a very precise point at which the system flips from self-cooling, dominated by what we call scientifically negative feedbacks, meaning dampening feedbacks. So one should know, when a scientist talks about negative feedbacks, it's the best thing we have. A negative feedback is very good because they dampen and cool and buffers, keeps the system stable. You push that across that very, very fine line, and the system irreversibly dominates by a positive feedback. And positive feedback sounds positive as good, but it's not. It's the reverse. It's self-amplifying. Positive means it strengthens, it amplifies, and in this case, it amplifies melting. It amplifies methane loss. It amplifies sea ice loss. It amplifies the changes. And you are in the region that is so white and so cold originally that the changes are happening so fast that the shifts are already starting to occur. You're sailing through a region where we're seeing signs of this flip occurring right as we speak. And to close this, the only reason why we scientifically cannot say exactly if the Greenland ice sheet has or has not tipped is that these are so complex procedures that there's an uncertainty range. So, for example, for the Greenland ice sheet, this physical point where the system goes from self-cooling to self-warming is scientifically, in the latest scientific update, assessed to be somewhere in the range between 1.5 and 4 degrees Celsius of global mean surface temperature rise. I mean, a very unsatisfactory broad range, but we have to admit it's complex science. But it can be now. It can be down at 1.5, and we've basically reached that point already today. And each of these tipping point systems need to have its own science to be able to find this precise biophysical point where the system shifts from self-stability to destabilizing itself. And I think, well, I'm curious to hear more about what have you been seeing on your journey so far.
Just a very quick summary of some of the tipping points that we are traveling through as a high level. And there's a great graph on this that we can show. But from Norway, we sailed across to Iceland, to the southern tip of Greenland, around what they call Cape Farewell, up the west coast of Greenland and onwards. The three tipping points that we have seen or been part of on the way is firstly the AMOC, the Atlantic Meridional Overturning Circulation Collapse, the Labrador-Irminger Seas Convection Collapse, and thirdly, the Greenland Ice Sheet Collapse. And in addition to that, which we're about to see tomorrow, we've seen a bit of it, is the Arctic winter sea ice. We're obviously seeing it in summertime, but it's obviously still connected. Then there's the boreal permafrost, which we're now starting to see, as well as the Nordic forest northern expansion, which we'll be seeing soon as we pass through northern Canada and Alaska. But maybe, Isak, we could turn to the Greenland ice sheet because there's some relevant things that we've seen as part
Absolutely.
of that.
Yeah.
And by the way, we should also mention that the 23rd of July, just a few weeks ago, was the hottest ever recorded day in human history. And it was on that day that we were sailing through Disco Bay.
Yeah, it was a great sunny day, but strange because you heard it a day after or so. We were having this beautiful day up in Disco Bay, and a few days after, when the news broke, it was just like, oh my God, it was actually the warmest day on Earth, and we were sailing through, watching these icebergs, and yeah, that's our connection to the Greenland ice sheet. Watching this just unbelievable. I don't even think it's comprehensible to us seeing it or for people hearing about it. The actual volume of ice that is being spat out by these glaciers, trying like funnels for the whole ice sheet, basically. So it was a very special thing to see.
Yeah, to put that in context, this glacier that runs from the ice sheet down through Ilulissat, or next to Ilulissat, which is this beautiful town on Disco Bay, that glacier itself produces 10% of all of Greenland's ice melt. And of course, all that ice is carving into that bay. And there we were sailing along from Disco Island across the bay through all these icebergs. I mean, it was stunningly beautiful. But we realized that, in retrospect, having heard that it was the hottest day ever, that we were probably watching the spot in the Northern Hemisphere that was the single biggest source of freshwater melt, because that is the single biggest source of the Greenland melt, the biggest outside of Antarctica. And there we were watching the world melt, basically, because as we were sailing along, you could see all these icebergs, the waterfalls are pouring off. Now, we know that icebergs melt. Now, that's what happens. But being there in that context of the hottest day ever, the single biggest source of ice melt into the ocean was really quite a compelling experience, wasn't it?
Yeah, it gave you a sense of the unstoppable force that nature is, and a connection to how this moving ice really can have an impact on the surroundings, because it was just such a grand thing to observe. So yeah, and this causes a lot of changes relevant for the whole Atlantic Ocean and hence the world. All of this meltwater.
Yeah, and one should, also something that very few people recognize is that, the energy imbalance that we've caused from burning fossil fuels and changing the environments over the past 200 years, what is called the energy imbalance on planet Earth, is only 2% of that heat that we have injected into the planet that is in the atmosphere that has caused this record warm day, 23rd of July, and everything we talk about as a climate crisis is what we measure in temperature in the air, and it's risen so far on average by 1.2 degrees Celsius, but we've touched 1.5. That's your point, Keith, that we've had these record temperature increase over the past 13, 14 months, which we actually don't even understand fully. However, that's only 2%. It's only 2% of the heat caused by our fossil fuel burning. 90% is in the ocean. So that's the biggest buffering system on planet Earth. But something like 3-4% is heat used to melt ice. So what you've just seen in Ilulissat and the spitting out of icebergs from Greenland Ice Sheet, not only is it a devastating sign of human-caused climate change, not only is it the prime driver of sea level rise across the entire planet, it's also a buffering system. It's actually like a panic move of planet Earth. It's a stress response that consumes energy. And it therefore hides a very significant part of our caused warming because of consuming energy when ice melts. The moment the ice is gone, that heat will go elsewhere, and it will go, of course, into the air, and it will accelerate warming on planet Earth. So it's like we should look at these icebergs and the ice melt not only as a sign of worry, but also almost as in a sense of awe, and just say, just what an incredible system this is that is applying its biogeophysics to try and buffer and stabilize. And I guess you've seen icebergs floating away also. I mean, correct me if I'm wrong, but I think they've been spotting these Greenland icebergs down to New York at times.
Yeah, I have to say that the Iceberg Experience has been an enlightening one for all of us. We were so elated to see our first iceberg as we came around Cape Farewell at the southern tip of Greenland. And of course, beyond that, we've seen literally thousands and thousands of them. But yeah, obviously the icebergs themselves are stunningly beautiful, all shapes and sizes. It's fascinating seeing the currents, the direction they take from the east coast of Greenland coming down the east coast, and then they wrap up around the southern tip up the west coast of Greenland. And so, for example, a Ilulissat that pumps out all those icebergs, they continue to go northwards, and eventually they turn back down on the east coast of Canada, of Newfoundland, and and Baffin Island and come back down towards New York. And in fact, the iceberg that sank the Titanic 110 years ago or so was in fact icebergs from that region coming all the way down through those currents. So on the point about currents, this is another big theme, which is the AMOC. The second big tipping point that we've experienced on the water. And one of the implications there is, one of the evidence points there, I think, is related to the Greenland Ice Sheet, is what I think is called the Great Cold Blob that's occurring in this region. That's something else that Alex has been very active with, is with our great friends at the Ocean Race, is using devices that measure the water temperature, the salinity, the CO2 concentration, etc., in the water. But yes, seeing that the change in temperature as during this journey has been fascinating. And maybe Alex, you can talk a bit about that, particularly around that experience around this southern tip of Greenland.
Yeah, so looking at the data that we've been collecting, plotting it on maps, it was very clear as we came out from the Irminger Sea and we started rounding around Cape Farewell. We saw how, most obviously, how the salinity rapidly decreased coming up close to Greenland, but also the temperature quickly increasing of the water. So we noticed a significant change coming up close to Greenland that very clearly is from the both from the current systems, but also from meltwater runoff coming into the ocean from the Greenland Ice Sheet.
You know, that's fascinating. I mean, you should be aware that this cold blob, this famous cold blob just south of Greenland, was a mystery for climate science for a long, long time. Because when you looked at global maps, and we've all seen these maps. They're all red. It's the ocean is warming across the entire planet because of our human-caused climate change. And then you have this cold blob suddenly, which one spot on planet Earth where the ocean water is actually getting colder. And that has been a mystery for a long time until it was understood that this is one of the three, let's say, engine rooms that runs the whole ocean conveyor belt, the circulation of water across the Atlantic, the Pacific, across the entire ocean system on planet Earth. And it's a well understood system because it's a thermohaline engine. It's driven by high density saline warm surface water coming from the Southern Ocean, so coming all the way down from the Southern Ocean on the Antarctic side of planet Earth, flowing up, reaching the Gulf Stream, following the east coast of the US, and reaching the southern tip of Greenland, where this heavy saline warm water releases heat to the atmosphere. And by releasing heat, it actually makes it livable in the parts of the planet where Isak, Alex, and myself come from, namely the Scandinavian region. That's what we call the effect of the Gulf Stream on the regional weather system. And then when this heat has been released, this heavy saline water sinks because it's so heavy. And the fact that it sinks is the engine that keeps this circulation moving, and then it reaches the bottom and it flows back slowly from the North Atlantic all the way down to the Southern Ocean, down to Antarctica. And this is what keeps the whole system circulating. Now, when the Greenland Ice Sheet releases these massive amounts of cold fresh water, it dilutes, of course, the heavy saline water. So by diluting it, it becomes less heavy. And this less heavy water sinks slower. And by sinking slower, it slows down the engine. And there are several studies that have shown that the AMOC, the overturning system, has slowed down by 15%. And that this is a big worry because when the AMOC slows down, it means it has several spillover effects. One spillover effect is that the whole so-called ICTZ, the convergence tropical zone that controls the regional weather systems that regulates the monsoon systems move further south. So what happens is that with a slowdown of the AMOC, you get a monsoon system that moves further south, which can explain higher frequency of droughts and fire over the tropical rainforest bed, but even potentially to the human parts of West Africa. That's one cascade effect. The second cascade effect, which is potentially even more worrying, is that by slowing down this whole system, you get more warm saline water moving slower away from the southern ocean, which can explain why the West Antarctic ice shelf is melting faster than expected, because you get, I mean, you've been there, Keith, you know this. Antarctica is different from where you are right now because Antarctica is ice on rock. So it doesn't melt from above, it melts from below, it melts from surface water lubricating the interface between the rock and the ice, which means that the whole system breaks and falls in big pieces like the Thwaites Doomsday Glacier is doing right as we speak. So in summary, what's happening in the Arctic via the AMOC drives or accelerates melting and warming down in Antarctica via the Amazon rainforest, which is impacted because of changes in rainfall patterns, regulated by the AMOC. Now, finally, there's a big scientific debate whether there's a risk of collapse of the AMOC. So the AMOC is now slowing down, and you've observed it through this cold blob. But the big debate is there a risk of collapse? And there's one scientific camp saying there's a very low risk of collapse. There's huge uncertainties, and it's unlikely to collapse, at least within the next, 100-200 years. Then there's another scientific camp, and I should be, clear that my institute, the Potsdam Institute for Climate Impact Research, is clearly in this camp where we have done research on the AMOC for 20 years, and we see more and more signs of a real risk of collapse. Nobody knows, though, when that may happen, but two scientific papers has come out recently, neither of them from the Potsdam Institute, one from a Danish group and one from a Dutch group, and they both conclude that we cannot exclude that the AMOC collapses even within this century. And if it collapses, that would, dramatically change weather systems across the entire world. The Scandinavian region would get quite abrupt reductions of average temperatures with at least 10 degrees Celsius. So you would dramatically change all living conditions in northern Russia, northern Canada, Scandinavia, Iceland, and you would accelerate sea level rise. You would have droughts and fires over all the rainforest systems. You would basically have a global impact of an AMOC collapse. But still, the jury is out. But what one has to recognize, which, I mean, you pointed earlier, Keith, to the historic maps. When you look at history, over the past 100,000 years, the AMOC has shut down, has collapsed at least twice. That we know with basically certainty. Everyone agrees on that. It may have actually partially shut down over 10 times. And so it is a system that is very sensitive because it is driven by this thermohaline engine, which is all to do with chemistry and physics of salinity and density. So it's a very, very fine-tuned system. And it's so determined because it's connected to the entire global ocean conveyor system. And I said earlier that we have 3 engine rooms for the global overturning of heat in the ocean. And so one is the AMOC, and then you have one just out of West Antarctica and one in East Antarctica. And so there's only 3 points, as far as we understand, that basically drives this whole system.
It's been wonderful with your 2 sons, Isak and Alex, as captain and first mate of Abel Tasman too, Johan. It's been a wonderful and thoroughly enjoyable experience from day one. And thank you for lending them out as the core crew for the trip. We've got 9 in total on board. We've got a great team of filmmakers and adventurers, and a key part of this overall expedition is to send the message that climate change is a scary change to the world, but it's also one that we can relish and enjoy in tackling the challenge. That this is something that humanity needs to grab, and we need to grab it in a way which is positive and optimistic, and enjoy actually the opportunity of solving it and doing it in a very prompt and very productive way. So we're certainly having a lot of fun on this expedition.
Oh, yeah.
And a lot of fun helping to communicate the science of climate change and the science. So, Johan, thank you for all your great work and for joining us for this session. And we'd love to post this on our website, on various other social media channels. And would encourage people to follow not just our own expedition, but also your great work. And as the director of the Potsdam Institute for Climate, the great research that you and your colleagues do is compelling and critically important for all of us, business, finance, and the community generally. So keep up your great work, Johan, and thank you for the great conversation. And thank you, Isak and Alex, as well.
Oh, thank you, guys.
No, thank you guys, and good luck with the continuation of your fantastic expedition. Looking forward to keep following you and tracking you, but also having these dialogues is also really valuable. So thanks for setting this up, and good luck.